In this lecture, let's start with the definition of sequence, and we'll look at some examples of sequences. A sequence is a list of numbers written in a definite order, A1, A2, A3, and so on. And since it is an infinite sequence, so we have the 3 dots at the end. That means we have infinitely many terms in a sequence. We call A1 the first term, A2 the second term, A3 the third term. So AN will be the nth term. And for the notation, we don't have to write out the infinitely many terms. We can denote a sequence using a bracket. We can denote a sequence like this, using this bracket, and inside we write AN. We will use a general expression to denote the nth term. Or, we could also write that as bracket AN, and outside of the bracket, we assign the first term of the sequence. Generally, n starts from 1, and it goes to infinity. Here's the first example. The formula for AN is explicitly given. The AN is the term given inside the bracket, which is n divided by n plus 1. So what would be the terms in the sequence? We know that n starts from 1. So the first term will be 1 divided by 1 plus 1, which is half. The second term will be when n equals to 2. So we plug into AN, we get 2 divided by 2 plus 1, which is 2 divided by 3. In the third term, we have 3 divided by 4, and so on. So the nth term would be n divided by n plus 1. And since it's an infinite sequence, so we use the 3 dot to denote that the sequence goes on forever. And you can note that as n approaches to infinity, the terms of this sequence approaches to 0. They get closer and closer to 0. In the second example, the formula is also explicitly given. The AN would be the terms inside the bracket, which is square root of n minus 3. But note that this sequence starts from when n equals to 3. So the first term, we plug n equals to 3 into the AN, which is square root of 3 minus 3, that is 0. Then the second term, we plug when n equals to 4. So square root of 4 minus 3, we get square root of 1, that is 1. Then the third term will be square root of 2, then square root of 3, and so on, until square root of n minus 3, and it keeps on forever. You may notice that as n approaches to infinity, this sequence, the number gets larger and larger. In the third example, this sequence we use another notation. When we have a recursively defined sequence, we also call that the Fibonacci sequence. So in this example, it's given that A1 equals to 1, A2 equals to 2, and for n that is greater than or equals to 3, AN equals to AN minus 1 plus AN minus 2, which also means when n equals to 3, A3, it equals to A2 plus A1, and A4 equals to A3 plus A2, and so on. Let's write out the terms for this sequence. The first two terms are already given. They are 1 and 2. And the third term, using the definition of AN, it will be 1 plus 2, which is 3. And the fourth term will be the sum of the previous two terms, which is 2 plus 3, that is 5. Then we have 3 plus 5, that is 8. Then we have 5 plus 8, that is 13. And the sequence keeps going. Let's look at the last example. The AN is negative 1 to the power of n. So the AN would be negative 1 to the power of n. Let's write out the terms of the sequence. First term would be when n equals to 1. So the first term would be negative 1 to the power of 1. That would be negative 1. Second term, we plug in when n equals to 2. So negative 1 to the power of 2. We have an even power. So the negative sign cancel and we get 1. Then the third term, we have an odd power. So we still have the negative sign. So third term is negative 1. Then the fourth term, we get 1. So we get an alternating pattern between negative 1 and 1. So in this example, we see that the sequence does not approach to any number as n goes to infinity. We can also represent the sequence on the graph. There are two methods. The first method is to mark the an on a single axis. Let's take the first example in this lecture. We had an equals to n divided by n plus 1. And we found the first few terms of this sequence. They were 1 over 2, 2 over 3, 3 over 4, and so on. So to draw this sequence, we first draw an axis. So this axis will represent the values of the terms. The first term is half. So on this axis, we mark the half, and this is our a1. The second term is 2 over 3. So on this axis, we mark 2 over 3, and that is a2. a3 is 3 over 4. a4 is 4 over 5, and so on. So from drawing out a sequence, we could clearly see if a sequence approaches to a number. From this example, we see that an approaches to 1. As n approaches to infinity, the terms get closer and closer to 1. And the second method to draw a sequence is to draw the sequence on the graph. The x-axis of the graph would be n, and the y-axis would be an, the values of the terms. And we mark the terms of the sequence as a dot. And they have coordinates of n and an. So the first term, its coordinate would be 1 and a1. Second term, it has coordinates of 2 and a2. The third term, coordinates are 3 and a3, and so on. So the nth term, it has coordinates of n and an. And the graph below shows the same example. The first term, it was 1 over 2. So it has coordinate of 1 and 1 over 2. The second term, when n equals to 2, the value of a2 is 2 over 3. So here is the second term of the sequence. Then when n equals to 3, we have 3 over 4. When n equals to 4, we have 4 over 5. And the sequence keeps on going forever. And we can use the same concept from calculus 1 using the limit. So we let an be a function that is only defined when n is positive and integer. Then to find whether a sequence converges, we can use the limit. So the limit as n approaches to infinity of an. Using this example, it will be limit as n approaches to infinity of n divided by n plus 1. So it is similar to finding the horizontal asymptote. We could factor out the n, and we see that this limit is 1. And that is the end of the lecture. In the next lecture, we are going to look at the convergence of a sequence. We are going to look at some properties and theorems to help us to define the limit of a sequence.